Hello and welcome to this video on the mean, median, and mode and their skewness. Distribution is said to be symmetric if a vertical line can be drawn at some point in the histogram such that the shape to the left and to the right of the vertical line are mirror images of each other. In a perfectly symmetrical distribution, the mean and median are the same values. Here we have a number of different distributions, all showing different shapes to them. On the left side here, we have a graph that is skewed left. All of the data values to the left have a low frequency. All of the values to the right here have a higher frequency. Recall that the mean is the weighted middle, or the balancing point. So if we were to try and find the balancing point of this distribution, it might be somewhere where I just drew it. And the low frequency values over here on the left might be stretching this balancing point further to the left. That's why we call it a skewed left distribution. Also notice here that the lower 25% of the graph, or of the box and whisker plot, are way farther to the left. Again, this graph is skewed left because it's being stretched to the left by these low frequency values. The histogram in the middle here is symmetric because what we have to the right of the graph and what we have to the left of the graph from this vertical line in the middle are the same. So it is symmetric in the same values. You'll notice here on the box and whisker plots that the left side and the right side are the same distances. The width of the interquartile range is the same on left and right side of the median because, again, the balancing point, the mean, and the median are the same values. And similar to our first picture before, sorry about this, I don't know why it's doing this. Hello, go away. When we have a skewed right distribution, the graph is shaded, or sorry, it's not shaded. The histogram has a lot of low frequency outliers on the right side and more of the higher frequency values to the left. Again, the weighted middle, or the mean, would be shifted to the right because all of these values over here are pulling it to the right. A good way of thinking about this is like if you were to hold out a heavy piece of luggage or something else, a heavy weight of some kind. If you hold it far away from your body is going to tilt towards that direction. So in this case, we're dragging the mean to the right. And I have a good visualization that we'll look at in a few minutes. Data can become skewed when it contains outliers. Again, outliers are data values that are quite different than the data values present. A measure is said to be resistant if it is not affected by extremely large or extremely small values. The median is said to be resistant because it is least affected by outliers. Sorry, I seem to be having some struggles with my technology today. All right, so now we have a picture here. We have a set of 3 pictures here. Oh my goodness. We have a set of 3 pictures here that are all frequency polygons, where the frequency would be on the vertical axis for all 3 of them. The data values, whatever they happen to be, are the x-axis values. The mean, the balancing point of this distribution, is being shifted to the left because of these low frequency values here. So the mean is going to be less than the median in a skewed left distribution. We also have this point on the graph. What can we call this point on the graph? Right, this would be the mode. Because again, the mode is the highest frequency, or the value that occurs the most often. So the value at the highest frequency would be the mode. In a symmetric distribution, the mean is equal to the median, which is equal to the mode. And in a skewed right distribution, similar to what we were saying before, these low frequency outliers, or these low frequency values way off to the right, are stretching the balancing point of the graph to the right. Again, the highest value here is the mode. And then we have an example. This example says, a small neighborhood that has 7 houses would like the town to pave their road because it is a dirt road. In the application, the town asks for the average family income for the neighborhood residents. The following incomes for the 7 families are as follows: $62,000, $58,000, $71,000, $45,000, $325,000, $85,000, and $78,000. Now, the application asks for the average family income. As we've talked about previously, there is no average in statistics. The average is actually a relatively poor way of discussing either the mean or the median or the mode. The average is basically a way of talking about a measure of center or a measure of central tendency. So let's take a second here to try and calculate the mean and the median. We can look for the mode, but I've done this one before and I know that there is no mode. There is no value that repeats. So let's take a second and make sure we know how to calculate the mean and the median. Here is my GeoGebra where I used the values. I left off the thousands place values for all of these, but we have that the mean is 103.8. Sorry, 0.4. And the median is 71. All right, so now that we have the mean and the median, we can talk about this. I have all of the data values plotted on a number line. The mean of 103 is somewhere around here. This is, again, the balancing point of the distribution. And if we look, there are 1, 2, 3, 4, 5, 6 values of the family incomes that are less than the mean, and 1 value for family incomes greater than the mean. Is the mean of 103,000, of course, a good representative for the family incomes? I don't think so. The median is 71. So somewhere between 60 and 70 is 71. Oh, the median is an actual value here. So we're looking right at that point here. If we look at the median, there are 3 values less than it and 3 values greater than. So since this application is asking for the average family income and not the mean or the median family income, I think that the town using the mean income of 103.4 or $103,428, I believe is what it was, we do not think that this would accurately reflect the family incomes for this neighborhood. And I have one more visual. Give me one second. We'll just switch over to the internet. We have this other visual here that shows a distribution with box and whisker plot on GeoGebra that has 15 data values in it. Now this link is available in the note packets. Feel free to click on the link and mess around with this if you want to. What I want you to notice is in blue, the median, and in red, the mean. I can grab any one of these points and shift it around, and as we move the points, we'll see what happens to the mean and the median. Other values may shift as well, but our main focus is on the mean and the median. What we'll notice is if I grab a point, let's say I grab this point 15, on the right of the mean, and I move it to the right, the median never moves. The median remains 9 the entire time, but the mean does move. If I grab a point on the left and I slide it to the left, again, the median never moves, but the mean does move. If I keep going with this point and I bring it way over here, what you'll notice is that the mean is being shifted to the left. This distribution is now a skewed left distribution because we have one low frequency value all the way to the left that is stretching the balancing point. It is stretching the mean towards the left. Now reset this. If I grab a point that's on the left and I slide it to the right, watch what happens when I cross the median. The median moves until I get to the next point, and then the median doesn't move again. The median will not get any larger than this, but if I keep going to the right, the mean will continue to get larger than this. So this shows how the mean is dramatically affected by outliers or low frequency values that are far away from the others, whereas the median only moves a little bit here or there. Again, that's why the median is said to be resistant.